Chemical reactions are where the fun happens in chemistry. It's also what keeps us alive. If we've eaten some food this morning, there's a chemical reaction going on in our stomach right now. Chemical reactions are all around us. So let's get into what are chemical reactions, chemical equations. And so first off, if we are going to represent a chemical reaction, we always need to remember that our reactants are going to be listed on the left-hand side and our products are going to be listed on the right-hand side. Of course, they're going to be separated with an arrow. And they're often represented by the idea that reactants react to form products in the forward direction. And we'll talk later on about how they go in the reverse direction sometimes too. Some of the symbols that we're going to use for chemical reactions, of course, you might see a solid reactant being used or a solid product being formed. You might see liquids, you might see gases, you might see aqueous solution, something that's been dissolved in water. Okay, and so let's give you a sample chemical reaction, and we're going to write this guy out. So it says, example, hydrogen gas reacts with oxygen gas to produce water. So remember, hydrogen gas is one of those 7 diatomics at standard conditions, assuming standard conditions here, because it's not indicated anywhere else. So this is going to be H2. It's going to react with oxygen gas, which is O2, and so those are our reactants. And they're also being consumed, and we're producing water, which is H2O. And there's our product, which is being made. And this is an unbalanced chemical equation, and so let's talk about how do we go about balancing this chemical equation. We need to balance chemical equations to show conservation of mass that occurs. So here's what's going to happen. We're going to use, if you remember from General Chem, chemical equations need to have equal numbers of atoms on either side of the arrow, and they're balanced by putting coefficients in front of atoms or molecules, and we do not change the formulas. So if we were to go back and rebalance this equation that's above, we have 2 hydrogens listed as reactants, and we have 2 hydrogens listed as products. So hydrogens are currently balanced, it's okay. Then we have 2 oxygens listed as reactants, but only 1 oxygen listed as a product. So I'm going to put the coefficient of 2 in front of here, and that 2 multiplies through everybody. So now we have 2 times 1 for the oxygen, so we have 2 oxygens now. But that has just changed the number of hydrogens we have as a product. We have 2 times 2, which is 4 total hydrogens. So we're going to come back over here on the reactant side, and we're going to place a 2 here, and it's going to be 2 times 2 for 4 hydrogens. So both, and we'll just double check it now. So now we have 4 hydrogens as reactants. We have 4 hydrogens as products. We have 2 oxygens as reactants, and we have 2 oxygens as products. So everything's balanced out now. Nice and neat. Okay, that was a pretty straightforward and easy one. We're going to look at a few other examples and some of the tricks that I'll show you of how to get these things to react properly or balance properly as well. Here's an example. We have methane reacting with oxygen to form carbon dioxide and water. We talked about methane in a previous video, and so everything in chemistry builds upon itself. So here's a perfect example. Methane, as you remember, hopefully, is CH4, and it's reacting with oxygen and also O2 diatomic. We're producing or forming, so these are our products now. We have carbon dioxide and we have water being produced. So we're applying quite a few things that we've learned previously in this equation. Now, one of the things that we can recognize for this balanced equation, and it works doing it just the old-fashioned way of kind of bouncing back and forth, balancing equations, but if you remember, methane is a hydrocarbon, and when hydrocarbons burn, they always need oxygen to burn. Well, most of the time they need oxygen to burn. We'll say for now they need oxygen to burn. And they're most of the time going to produce carbon dioxide, and they're most of the time going to produce water. These are our constants. The water produced, the carbon dioxide produced, and the oxygen produced. The only thing that we're going to be seeing that changes is who is the hydrocarbon. And we talked about the different alkanes as well as the hydrocarbons and alcohols before. So that might be the only thing that changes here. Now, if you can recognize this is a hydrocarbon burning an oxygen to form carbon dioxide and water, I say we have a hydrocarbon reaction, and we're going to balance it CHO. And what does balancing it CHO mean? It means we're going to balance carbon first, hydrogen second, oxygen last, and that typically gives us an easy way to balance this equation. So let's balance this CHO because it's a hydrocarbon. So we have one carbon on our reactant side, and we have one carbon on our product side. And so the carbons are currently balanced, not a big deal. On our reactant sides, we have 4 hydrogens. On our product side, we have 2 hydrogens. So I'm going to put a 2 in front to balance out that. And then we're going to finish it all up with our oxygens. We have 2 oxygens here. We have 2 here. But we have to add in the 2 times 1 over on this side. So we have 2 there. So we have 2 plus 2 for a total of 4 oxygens on this side. And we want 4 oxygens on this side. So let's go ahead and place a 2 in front of here. And so now we're balanced. Now I'm going to show you a trick on a CHO reaction in a little while about how to get it when things come out a little odd. And so that'll be coming soon here. Look out for that. The next one, I want to throw in some polyatomics. Hopefully in this reaction you can recognize there is an NO3, and if you've been studying your polyatomics as you should recognize that as a nitrate. Over here on the other side we have an NO3 too, also a nitrate. When I see polyatomics that they're the same on both sides of the equation, I like to treat them as a complete unit. I like to count the number of polyatomics. So I could say here I have 2 NO3s, but on this side I only have 1 NO3. It's also possible to count individual nitrogens and oxygens, just easier to count NO3s. So let's start with the beginning here. We have 1 lead and we had 1 lead, they're balanced. Obviously now we're going to jump into the NO3s. I just kind of work my way down the line here. So if 2 NO3s on the left, 2 nitrates, but only 1 nitrate on the right. So I'm going to place a 2 in front of this to give me now 2 nitrates on both sides. Now I have here 2 potassiums and only 1 potassium on this side. So I'm going to go ahead and place a 2 there, balance out the potassium. I'm going to count the iodides. There's an iodide there. So I have 2 iodides, 2 times 1 is 2, and we have 2 iodides there. So now we're all balanced, and we would read this coefficient as 1, 2, 2, 1. If we leave them blank, that is assuming it's 1. Here's another reaction that sometimes gives students a hard time, and there's a way to adjust for this. And here's what we're going to do. So we have sodium reacting with water to produce sodium hydroxide plus hydrogen gas, a neat reaction that can cause explosions and things like that if you add too much sodium to water. And so here's one of my tricks with this reaction. If I see a water on one side and I see a hydroxide on the other side, I'm going to balance this a special way. Now you can balance the same old way that everybody always balances it, just by balancing sodiums and sodiums and oxygens and oxygens. This is just my trick, and it works. If you want to use it, you can. If I see water on one side and a hydroxide on the other, I'm going to rewrite the water as H-OH. It means exactly the same thing as water. It's still going to be 2 oxygens and 1 hydrogen. The only reason I like to do this is then I take this hydroxide and I balance it separately off of this hydroxide. And then I take the hydrogen and I balance it separately off of that hydrogen. Now, if I separate it out like that, it just makes it easier to balance. So let's start at the beginning. We have 1 sodium, we have 1 sodium. Sodiums are currently balanced. Okay, I'm going to ignore the water for the moment, and I'm just going to balance it off of HOH. So looking at just my H here, just this H here, and if I balance it off of that H there, then I have 2 H's on my product side, 2 hydrogens on my product side, but only 1 hydrogen on my reactant side. So I'm going to go ahead and place a 2 in front of that, just like that. Now, I now have, okay, we've done that. Now I have 2 hydroxides here, but I only have 1 hydroxide there. So I'm going to place a 2 there. Now that changes my sodiums, so I'm going to go ahead and place a 2 there. And now I'm balanced. So my correct coefficients are 2, 2, 2, 1 for the hydrogen. Okay, that's just a trick way, a little trick of the trade that I like to use when I see water on one side and a hydroxide on the other. Of course, doing it just the old-fashioned way of counting atoms works perfectly fine too. Okay, it looks like I have another couple hydrocarbon reactions, and this is the same reaction. Looks like I rewrote it again. Let's ignore that reaction. We've balanced it up above, but this next reaction is interesting, and here's why it's interesting. Again, this is a hydrocarbon reaction, reacting with water, or with oxygen rather, to form carbon dioxide and water. Okay, so again, these are the type of reactions that I like to balance show. But there's a trick to this one, and I'm going to show you the trick in a second here, or there's a little twist to it. So I'm going to start off balancing carbons first. So my carbons on the left-hand side, I have 4 of them. On my right-hand side, on my product side, I have 1. So I'm going to place a 4 there. Okay, so now my carbons are balanced on both sides. Hydrogens come next. On my reactant side, I have 10. On my product side, I have 2. So I'm going to place a coefficient in front of here. When multiplied by 2 gives me 10, and that would be 5. 5 times 2 is 10. So now we have 10 hydrogens on both sides. Okay. All right, here's the trick on the last part. Watch what happens here. We know that on our reactant side, we only have 2 oxygens. Watch what happens on the product side. We have 4 multiplied by 2, so here we have 8 oxygens. Then we have 5 multiplied by 1, we have 5 oxygens. When we add 5 plus 2 together, you can see where we're going with this, we get 13. Okay, now I cannot put a number on the reactant side when multiplied by 2 equals 13. Well, actually I can. I'm going to put a decimal. I'm going to put 6.5. Okay, because 6.5 when multiplied by 2 gives me 13. And technically we're balanced right now, except there's a rule in balancing equation. And the rule is, and it's slightly flexible rule, as we'll see later on in AP chemistry, but the rule is your coefficients must be lowest whole number ratios. Now we'll find out later in AP chemistry that sometimes they like to illustrate coefficients as maybe fractions, which is what we have here. But for now, let's go ahead and make this the lowest whole number ratio. And we'll talk about what that means here in a second as well. So to make this the lowest whole number ratio, I'm going to multiply this whole expression by a number that will make all of these numbers a whole number. So let's multiply the entire expression by 2. And what I mean by multiplying the entire expression by 2 is I mean that we want to make sure we multiply every single atom or compound by 2. So I'm going to multiply the C4H10 by 2. I'm going to multiply the 6.5 by 2, which gives me 13. I'm going to multiply the 8 by 2, which gives me 8. And I'm going to multiply the 5 by 2, which gives me 10. So now we have 2, 13, 8, 10 as our correct whole number, lowest whole number ratios. Now, if we look at it, can we reduce those coefficients down? And the answer is we cannot. We cannot divide them all by 2 because that would get us back to a fraction. Okay, but let's take a look at something real quick here and see when we should reduce. Let's go back up to this reaction above, which we had already balanced this reaction here that I just erased. Now, when we balanced this reaction before, I believe, let's see, 2, 2. We had this as correctly balanced. Carbon, carbon, hydrogen, hydrogen, 4 oxygens, 4 oxygens. This is correctly balanced. Now let's say if we were going through and balancing this equation, we balanced it so that it was actually 2, 4, 2, 4. Now, for right now, we want lowest whole number ratios. Now, there will be a reason later on in AP chemistry that we might have a reaction that looks like this, but for now what we want is we want lowest whole number ratio. So let's go ahead and make this the lowest whole number ratio by reducing. And when we reduce this down, obviously we're going to divide everybody by 2, which will give us 1, 2, 1, 2 as our lowest whole number ratio. So for now, let's say we want lowest whole number ratios always. Okay. The last thing I want to talk about is how to interpret a balanced chemical equation, and this is going to be important later on for us. And so let's take a reaction like this, and we're going to just do an interpret real quick. We'll balance it first real quickly here. And so 2 nitrogens, 1 nitrogen, we'll put 2 there. We have 6 hydrogens, and we're going to put a 3 there. Okay, so now we're balanced. Now, we can interpret this a couple ways. One, we can say here we have one molecule of nitrogen right there. And one molecule of nitrogen is going to react with 3 molecules of hydrogen to produce 2 molecules of ammonia. And that's a good way to look at things. We can also look at this in terms of moles. Moles we remember from general chemistry, and we'll get into that in our next video. And we could say that we have 1 mole of nitrogen reacting with 3 moles of hydrogen to produce 2 moles of ammonia, NH3. So those are a couple different ways that we can interpret chemical reactions. Going down the road, we'll incorporate in molecules and Avogadro's number, and of course grams. That's coming in our next video. So just for now, we'll talk about molecules and moles in our interpretation of balanced equations. Okay, that's the video. There will be a worksheet as well as an online quiz that goes along with it.